Good night, Mister. We are the group B, and we are going to talk about the noble gases.
The land covers 3/4 of water that 97% of correspond to the oceans. So this is the reason for that surface of the sea there is a constant exchange of gases between and the air and the water. So this this gases exchange is important and fundamental to separate consistent of the ocean because the biodiversity existing in the sea wouldn't be possible without the chemical cycles that occur in it. The most important is the photosynthesis.
Well, my name is Paula. I'm going to talk you about the physical aspects of the gases. First, we have Gay-Lussac law that is about when you have a constant volume, the pressure will be directly proportional to the temperature. Another law is the Henry laws. This law is about how the solubility of a gas behave. For example, this law announced that the partial pressure is directly proportional to the solubility of the gas, and you have to add a constant of proportionality. Another very important aspect is that gases behave in sometimes sometimes in a difficult way. They behave like something that we cannot understand, but these state equations as PV equal nRT, that says the product between pressure and volume is equal to the amount of the gas molecules, temperature, and the volume. And this equation is the simplified version of some of the equations of van der Waals, Dietrich, and these persons that try to understand and measure the behavior of the gases.
About the application of water masses, noble gases are useful for studying processes in the ocean environment because they have inert behavior. Noble gases are used as tracers of water masses and ocean surface processes. Noble gases measurement have been used to investigate the air-sea gas exchange and the balance that exists during the formation of water masses. Helium-3 isotope had been widely used in ocean circulation study and also to quantify ocean lithospheric interaction. Also, noble gases can be combined with biological active gases such as oxygen and nitrogen to quantify rate of biologic production and denitrification. Helium, neon, and argon have been provide information on cryospheric ocean processes, such as sea ice formation and basalt melting of glaciers.
The amount of gas can be dissolved in seawater is determined by variables like temperature, salinity, atmospheric pressure, evaporation, and other variables. The different salt concentrations of the elements provide special salinity characteristics and therefore water density, which plays an important role for biochemical and cycle equilibrium process of the ocean. In the ocean we have in a little quantities gases nobles, and these gases nobles are inert, and there are five: helium, neon, krypton, argon, and xenon. In ocean studies, noble gases have been used for the exchange of gases between the air of the sea, allowing the displacing separate of flowable component of the fused gas exchange and the students balance during the water information. Argon and helium and neon used to quantify ocean lithospheric interactions. They can also be mixed when the chemical activate gases like oxygen and nitrogen to quantitative biology and denitrification rates. Finally, novel gases are potentially unambiguous tools for detecting and to the quantitative the relative conservations of the test process of seasonal land creation and destruction, as well as significantly modifying water density and helps improve to the differentials of salinity in the oceans.
I'm going to talk about the distribution of noble gases in the ocean. In this first graph, we have the Atlantic Ocean and the Pacific Ocean. If we see the Atlantic Ocean, we can see that in the mixed layer there is an undersaturation of noble gases. As we go close and deeper into the thermocline, these become supersaturated and stay in the range of supersaturation throughout the water column. In contrast, in the Pacific Ocean, we see a mixed undersaturated layer that starts to pick up in concentration levels as we reach the thermocline. But as we go under it, we can see the diminish of the concentration, making it undersaturated. This is a distribution of noble gases in the deep South Pacific Ocean. Station 1 started at the equatorial line, and station 2 and 3 go souther and souther, and we can study this. You can see in all three of them that there is a pattern where the noble gases start to diminish and then pick up as we reach the bottom of the ocean. This may be due to the plate tectonic activity of the South Pacific Ocean, as this is a very active zone full with oceanic volcanoes and ridges that the earth crust, and there is an influx of noble gases into the ocean. The interesting thing that happened is that station 1 is very close to the Cornwall Current. The Cornwall Current is known to be cold, about 2 to 13 degrees Celsius, and full with nutrients and gases. So, in this next graph, we can see how these are distributed in the station 1. We can see a dotted line. This represents the concentration or saturation levels we expect of a gas at this temperature. The crosses are the concentrations measured in these temperatures. And we see that as we go deeper into 13 to 12 degree range, these two levels align themselves almost perfectly, which means that even though the station 1 wasn't exactly in the Cornwall Current, it has an effect, whereas there is mixing of the waters, the sea waters, with this current, and the noble gases have a new influx coming from the water currents. This could also explain the behavior we saw in the last picture.